In this little presentation, we will talk just about the nomenclature and properties of organohalides. These are also called haloalkanes because there's a halogen on the. So first, nomenclature, okay, and then we'll do the properties. So we can start from the smallest alkyl halide or haloalkane, starting from methane. Methane is the smallest alkane possible. So if you substitute a hydrogen with a halide, then you get a haloalkane. So for example, with the chlorine, you would get chloromethane. If you substitute with bromine, then you get bromomethane, and then iodomethane if you had CH3I. If you had 2 or 3 substitutions of the halide on methane, then this is what it would be. So if you had CH2Cl2, it would be dichloromethane, CH2Br2 dibromomethane. And then if you had 3 substituents or 3 hydrogens replaced by chlorine, it would be trichloromethane. In case of ethane, you can have 1 substituent, in which case you have chloroethane. And if you start having 2 substituents, then you have to give the location. So for example, in this case, it would be 1,1-dichloroethane because you have to specify the relationship between the 2 chlorines. So then the next isomer I have here for you is 1,2-dichloroethane. Okay, so the relationship is slightly different between these two. So you have to do the numbering. And then if you have 2 halides, 2 different halides, then you go ahead and number according to alphabet, and you name also according to alphabet. Okay, if it was longer, you would still give preference to the bromo because it's alphabetically lower. So if you have long chain alkanes though, then it's slightly different. Halides have no particular preference over alkyl groups. Okay, so it's really just a matter of finding the nearest substituents. Okay, whether you have an alkyl or a halogen, it doesn't really matter. The branching gets preference, not the substituent. Okay, so really anything goes here. The only thing you have to make sure is that you name the compound alphabetically. Okay, so for example, in this case, since your branching is starting from the left hand side, you will start the numbering from the left hand side. However, because we have bromine here, your naming will start from bromine. So this is 5-bromo 2,4-dimethyl heptane, and then here now, because bromine is 2 does not mean you start from there. Bromine is 2 because the branching is starting from here. Okay, and so just a slightly different isomer here. If you have 2 substituents equidistant from each other, or equidistant from the terminal carbon, so both of them are 2, then you will give the preference to the lower alphabetical substituent. Okay, so if there was a chloro and bromo would still get preference because it is starting with B, okay, instead of C. So that's how it goes if you have 2. So which means that really whether you have an alkyl group or a halogen, it doesn't really matter. Alphabetical preference is the best. Here are some more examples for halides. You have a little bit different kind of functional groups over here. Alcohols and alkenes get preference over halides. Okay, so for example, if you have an alcohol in there too, then the chlorine will, the alcohol will get preference. Okay, so the relationship here is trans because one is going up, the other one is going down, hydrogen. And then there's 2-chloro-cyclohexanol. You don't have to say 1-cyclohexanol because it's understood that alcohol has the preference. Okay, so trans 2-chloro-cyclohexanol. And then here, again, if you have an alkene gets preference. Now remember, you have to include the double bond in your nomenclature. Okay, so 1, 2, 3, 4. So 4-bromocyclohexene. Again, you don't have to give the number for cyclohexene because it's understood. Okay, that the double bond is on 1, but remember to include the double bond. Some of the common names for alkyl halides and alkanyl halides, which means that if you have double bonds and triple bonds, then for double bonds, this one is called the vinyl chloride because this is the vinyl group. If you remember 2 carbons with a double bond, it's called vinyl. And so this is vinyl chloride, and here is allyl chloride because 1, 2, 3 carbon fragment with a double bond is called allyl group. And so this is allyl chloride. Okay, the IUPAC name of this one would be 3-chloropropene because 1, 2, 3, that's how the nomenclature goes. Okay, so the chlorine is on the 3rd carbon. So these are the common names if you have double bonds. And then the polyhaloalkanes, we did them in the previous slide also, but I just want to mention it again because these are quite common and you will see them a lot. For example, dichloromethane, you see that in the lab a lot, okay? But this is also called methylene chloride, and it's called methylene because of the CH2 group over here. You all know about the CH3 group. The CH3 group is the methyl group, but the CH2 group is called the methylene group. It's a little confusing because when you think of ene, you think of double bonds, okay? But please don't think of double bonds over here. So this is methylene chloride, which means this is the methylene and then chloride. So dichloromethane is of course the IUPAC name. And then the trichloromethane, which also we did in the previous slide, is also called chloroform. If you had 3 bromines over here, it would be called bromoform. If it was iodine, it would be called iodoform. Okay, so those are the common names. And then here is methylchloroform and then trichlor. Now, some of these you may not really encounter a whole lot, but you might hear them, okay, once in a while here and there. So in that case, don't panic, just look it up. The physical properties of alkyl halides, first of all, the boiling points. Most of the alkyl halides are going to be liquids because of the dipole-dipole forces. Okay, so for example, even in the smallest alkyl halide, okay, which is bromine with methane, so bromomethane, even that one has a boiling point of 4, which means that it is a liquid. It has a very low boiling point. That's a whole different thing. But there are some dipole-dipole interactions, and because of that, you will have a little bit higher boiling points. Okay, and so the haloalkanes will have some dipole moment, okay, because of these electronegative elements. Now, if we go from something like CH3F to CF4, which means tetrafluoromethane, then the dipole moment will be 0, but the molecule will still be polar in some ways. Okay, you will still experience some of the dipole-dipole forces, okay, in this case. So you have to kind of understand those two aspects of haloalkanes. So then the density of haloalkanes, this is something that we should talk about. We don't talk about it so much for alkenes and alkynes and so on because they all are the same way. But haloalkanes are different because as soon as we start getting down to chlorine, bromine, and iodine, the size of the atoms increase, okay, a lot, and the weight of the atom increases a lot. And so because of that, almost all the haloalkanes will have higher density than alkanes, not almost all. Okay, all haloalkanes will have higher density than alkanes. And because of that, they also have a little higher density than water sometimes, okay, because they're very heavy molecules, all right? So if you look at the density of these substituents over here, so the CH2X2, this is if X is chlorine, so dichloromethane is 1.3, chloroform is 1.4, and then carbon tetrachloride is almost 1.6. So the density will keep increasing because the weight of the atom, the halogen, is increasing. So you can see over here, by the time you get to tetraiodomethane, it's a very, very heavy compound. Okay, and so the density is higher than alkanes as well as water. Regarding the solubility in water, it's going to be very little. The only intermolecular force here is the dipole-dipole interaction, which is also very less. And so eventually the dispersion forces will take over, and dispersion forces do not go very well with hydrogen bonding and dipole-dipole. So therefore, as the molecular weight increases for haloalkanes, the solubility decreases. So solubility in general is very low. Some of the applications of alkyl halides that you should be aware of. These are very common compounds. Okay, alkyl halides, you will see them a lot in anywhere, and sometimes you're not even told that they're there. So for example, we see them in lab all the time as solvents. Dichloromethane is one of the most common solvents that you will use. So dichloromethane and chloroform, okay, two common solvents. Then a lot of the alkyl halides are very good starting materials for substitution reactions. So yes, then you use the alkyl halides. Chlorofluorocarbons have been used a lot as refrigerants and propellants for aerosols and also for dry cleaning. They're generally very good for degreasing, degreasing meaning removing the grease, obviously. And so They're very, very common here, but there is a problem with the chlorofluorocarbons, the CFCs, because they are known to deplete the ozone layer. So now they actually are not used in the US, and there are a few countries who have signed a pact of not using CFCs, so they've banned CFCs. But they're still around, okay, because other countries still use them, but that's the problem with CFCs, is that they deplete the ozone layer. But they still have their functions, okay? And so in some cases they're still used, but not as commonly as they were used before. Um, Alkyl halides are also very good materials for polymers. And in here, when we're talking about alkyl halides, it's not just alkyl halides. These are also including the alkene halides, okay? And so in those cases like vinyl chloride, ethene, those are very commonly used starting material for polymers. So we will talk about that when we are kind of all finished with everything here. And then some of the alkyl halides are very good fire retardants. And they're called fire retardants because they just remove the oxygen, okay, from the environment. It's not like carbon compounds are not combustible. They are combustible. But what they do is that they just overwhelmingly remove oxygen from the environment, and so the fire is actually put out. And so they're very common fire retardants. So you might find them, for example, in fire extinguishers in labs and so on. There are other uses for alkyl halides. Not all of them are covered over here, so as you go on, you will learn more. There are not very many key concepts over here. You need to know about the nomenclature of alkyl halides, the common and IUPAC, and you also need to know the physical properties. So you can compare all across from alkanes, alkenes, alkyl halides, and yeah, that's about it. That's about all we're doing.